Good afternoon and welcome to the CERIAS Security Seminar from Purdue University. Our speaker today is Dr. Bharath Samanthula. He's a research associate with the Cyber Center here at Purdue after getting his PhD 2 years ago at the University of Missouri-Rolla. He's also a visiting assistant professor with the computer science department here. His research interests are in personal privacy, information security, applied cryptography, and data mining. Current research focuses on devising policy-enhanced solutions for various data outsourcing tasks in cloud computing and social networks. His topic today is security with privacy. Right?
Thank you for the nice introduction, Bob. So first of all, good evening to everyone. So the topic of today's talk is security with privacy, a research agenda. Here is a brief outline of the for today's presentation. First, I will talk about motivation behind my research and the problems I am trying to solve. Then I will give a high-level view of two important key technologies, namely big data and cloud computing. And then I will discuss about two important problems, namely like privacy-preserving data management and privacy-preserving data analytics under the cloud environment. There has been a lot of research along these lines for the past couple of years, so it is very hard to cover all of them. So I will just discuss some important work along that direction. Finally, I will conclude the presentation with some discussion on future work. So we all know that organizations are collecting huge volumes of data in their daily business operations. For example, IBM itself has been generating 2.5 quintillion bytes of data per day. I mean, this is roughly equal to like 2500 petabytes of data per day. Most of the times, this data is being collected from so many data sources, such as sensors, weblogs, GPS signals, and social media. Another good example is Facebook, Twitter. They are collecting around like 15 to 100 petabytes of data every day. So what is big data is all about? It deals with efficient management of large, complex, and growing data and extracting useful information from it. So here, a survey by Oracle shows that data around the world has been growing at a rate of 40% annual rate. Probably by 2020, we'll see around like 45 zettabytes of data. I mean, zettabytes means like 10 raised to the power of 21. So that's a very huge volume of data. So there is a very strong need for the research community to develop specific techniques, how to store, manage, and analyze big data. So since we are generating large volumes of data in so many fields, big data is not only important in computer science, it is also useful in so many applications. For example, in physics, biology, finance, etc. I mean, as you can see on the right side of the slide, there are many papers related to big data in so many fields that shows the broad impact of big data actually. Having seen the potential of big data and to boost further research in this field, the US President Obama administration has announced Big Data Research and Development Initiative in 2012 actually. So the NSF has a separate solicitation for topics or proposals related to big data, and they are going to fund millions of dollars who are doing in the research in this particular area. So there are many big challenges associated with big data, and I have highlighted some of them here. But the main focus of today's talk is security and privacy. So by privacy, what I mean to say is whatever sensitive information or personally identifiable information associated with any individual should not be disclosed to unauthorized persons. So in this knowledge-driven world, very often organizations need to share their data with outside world, right? But data is one of the most valuable assets by any organization. So they cannot freely share their data with other persons, right? There are many factors associated with that. One is privacy, and also due to various government regulations, you cannot freely share the data actually. So how can you share or analyze the data with other parties? A common technique is to anonymize the data before releasing it. But previous research shows that we can combine the anonymized data with some publicly available data sets and then extract some useful information from it. So anonymization is not a very powerful technique. So the key question here is how to share and analyze such large volumes of data in a very privacy-preserving manner. So the Executive Office of the US President has recently released a note emphasizing the need for reconciling the research in big data by taking privacy into consideration. So we have seen a lot of research developing new tools for big data, but none of them take privacy into consideration. But privacy is a very big factor, and the US government is emphasizing that we need to change our direction. Perhaps cloud computing is one of the key technology to store, manage, and analyze big data. Basically, we want to take the powerful computing facilities provided by the cloud computing environment and solve various big data applications. So this cloud computing, it allows organizations or even an individual to outsource their data as well as computations. So this is especially useful, right? I mean, if a user do not have proper resources, he can simply outsource the data and ask the cloud to perform certain tasks, and he can pay the money for the cloud provider. But what is the problem? So cloud computing, I mean the cloud provider actually, he's a third party, right? So we cannot trust him fully. So what do data owners or the one who is outsourcing the data do is, he will encrypt or transform the data in somehow and then export the data to the cloud. But again, there are some issues associated with that. Once you transform or encrypt the data, how can the cloud do the operations? If you have plain text data on the cloud, it is very easy to do operations. But you have some transformed or encrypted data stored on the cloud, it is not so easy to perform operations, basic operations on the data. So in the past decade, people have proposed a lot of solutions actually to handle like how to store and analyze data in a privacy preserving way. But the solutions have several issues actually. Since we are talking about big data, the solutions need to be scalable, right? Most of the solutions, they are applicable only for small set of data sets. So they are not applicable to big data. And also most of these solutions, they do not ensure standard security guarantees. That is mainly because of efficiency reasons. If you want to have an efficient protocol, you need to compromise security. So it's like trade-off between efficiency and security. So my focus for the past couple of years is to develop efficient and effective privacy enhancing techniques, tools, and frameworks on how to manage and analyze big data actually. So I will also outline some research challenges that will be helpful for the cloud community to further boost the research in this field. So next I will discuss some important problems that I am trying to solve. So in general, the privacy enhancing technology that I want to use or that I want to develop depends on the intended use of the data, right? And this intended use of the data varies from task to task. So here I have categorized two important problems. One is privacy preserving data management, and the other one is privacy preserving data analytics. We're going to discuss about each of these in detail. So the basic framework for the privacy preserving data management is shown in the slide. So we have three entities. One is the data owner, the second one is the cloud provider, and the third one is a set of users. So what is the goal of the data owner? He just want to outsource the data as well as the DBMS functionalities to the cloud. And the role of cloud is to manage this data efficiently and provide the services on behalf of the data owner. And of course, the goal of the client is to access this data on the cloud in a privacy preserving way. So there are two main issues associated with the privacy preserving data management. One is fine-grained access control, which means that different users can access different parts of data, right? It's not like every user can access all the data. If you take, for example, any credit card company, you can access only your account information, right? You cannot access everyone's information. So you need to have a fine-grained access control mechanism in place. The second issue is supporting query processing. So this is a basic operation we have been seeing in relational databases, right? So whenever I was looking for some information, I need to issue a query, and the server will extract that information and send that to me. So query processing is also a basic functionality that need to be supported. So again, the goal here is we need to develop a very effective PPDM framework. So what do we mean by effective? Because there are so many functionalities associated with databases, right? So those functionalities should also be supported in my outsourced environment. Otherwise, it is not complete, right? So it should be effective, efficient, and the solution should be scalable for big data applications. So privacy preserving data analytics. So just storing the data and managing the data is not useful, right? If you take any company, I mean, given that they have large volumes of data, what they try to do is like they want to extract useful information, right, which they can use for their business growth. So extraction of information from this big data is a very crucial problem. So unlike, similar to privacy preserving data management, like database as a service, here we are going to outsource data analytics. For example, if you want to do a data mining task, for example, clustering, you can send the data to the cloud and ask the cloud to do the clustering task on your behalf. But that should be done in a privacy preserving manner, which is a very hard task actually. This is especially useful, right? If you have resources, you can do the task on your own computer actually. But what if you are dealing with big data? For example, if you have a researcher from biology, he may not have proper resources, and also he may not have proper knowledge about how to do the data mining. So in those cases, you can just export the data to the cloud and ask the cloud. So basically, there are two different settings under PPDA. The first one is the single user setting, and the second one is the multi-user collaborative setting. So the single user setting is the most basic setting. So we have a user, and he wants to perform some data analytical task. So he will encrypt the data first, or transform the data somehow, and send the data to the cloud, and also send what kind of analytical task he wants to perform. So the cloud will do. That's a difficult task actually. The cloud will somehow do the task and send the result back to the intended user. So this is a more interesting setting actually, multi-user collaboration setting. So here we assume we have a set of users, and each user has a database actually, data set or database. And they want to perform data analytical tasks on their combined data set. So one good example can be like if you have multiple hospitals, each hospital can have some patient's data, and patient data contains a lot of sensitive information, right? Like your health data, what diseases you have, your SSN information, and all those things. So most of the time, these hospitals, they don't want to share the data with other hospitals, but they want to do some kind of analysis. So all the hospitals can need to do some kind of analysis on their combined data. So how they can do? We have some traditional solutions in the literature. We refer to them as privacy preserving data mining. But in privacy preserving data mining, all the users has to collaborate and involve in the process. So they have to utilize the resources actually. But I want to have a different solution. I want to outsource this complete task to cloud actually. So in this setting, what users are doing is each user will encrypt their database or data set and send it to the cloud actually. Then the cloud will somehow do the task on this encrypted aggregated data. But how to do this task, that's the main challenge actually. Encrypting the data and outsourcing is not a big issue here. But how the cloud is going to do that, that's the main thing. And we have to do that in an efficient manner. So before going into the details, let us quickly go through some observations here. If you take any task, actually any price representing data mining or data analytics task, most of the solutions are constructed based on some basic security primitives, such as secure equality, secure comparison, etc. So these are the building blocks actually. So I mean, it is obvious, right? I mean, if you have more efficient basic primitives, the final solutions resulting from PPDM and PPDA will also be efficient actually. So the basic, intuition is we need to develop more efficient solutions to these basic primitives actually. Another interesting observation is we know that cloud computing supports parallel and distributed frameworks, right? So if you are not utilizing these frameworks, what is the point of using the cloud actually? If you are just using a single node and running the whole task on it, then even though the machine is powerful, it might take few hours, right? It depends on the task. But since we have cloud is supposed to have enough resources, why don't we use them? So you need to develop the solutions in such a way they are parallelizable actually. If your solution is not parallelizable, then you cannot use those resources, right? So first you need to make sure that your solution is parallelizable and ask the cloud to implement this in a cluster of nodes actually. This is especially useful for big data applications. I mean, if you have like 1 million data records, you can distribute this 1 million data records on a cluster of 100 nodes and do the task in a somewhat better way actually. So next we will discuss about this basic primitives I have just mentioned. So as we discussed just now, these cryptographic primitives are the basic building blocks of any task actually. So here I am specifically emphasizing cryptographic because that ensures maximum security guarantees. But we can also design solutions that are non-cryptographic, but they do not offer maximum security. For example, once you outsource the data to the cloud and you want to compare two numbers, for example, if it is plain text data, the cloud will do automatically, right? Since the data is in plain text. But since we are encrypting the data, how can the cloud will do secure comparison, secure equality, and so on? For that, it can utilize the existing solutions actually. So if you assume that the data is encrypted using fully homomorphic encryption schemes, I don't know like how many of you are aware of fully homomorphic encryption schemes. So fully homomorphic encryption means if you encrypt the data using these schemes, you can do all operations within encryption actually. For example, if you have like encryption of 4 and encryption of 5, using these two values, you can compute encryption of 4 plus 5. You can also compute encryption of 4 multiplied by 5 and so on. So if you can basically do multiplication and addition, you can do any operation, right? Because almost all the operations are based on multiplication and addition. But the problem with these kind of fully homomorphic encryption schemes is they are not practical actually. Even if you take a small data set, the solutions are still not practical. So then obviously for big data applications, their uses are decades away actually. So that is the reason why people have been developing alternative solutions. So one important encryption scheme is like homomorphic based schemes. What homomorphic encryption scheme do is like it will either support addition or multiplication, but not both actually. And of course, we need to develop, as I mentioned earlier, we need to develop parallel solutions, right? Otherwise, there is no way we can handle big data applications actually. I mean, as far as I know, there are no like current works that handle big data applications in the privacy preserving way. So all these solutions, even the solutions based on homomorphic, additive or multiplicative homomorphic encryption scheme, they are not suitable for big data applications because they are not parallelizable actually. So people are currently focusing on developing parallelized solutions actually. So in one of our recent works, I mean that got accepted at IEEE ICD and IEEE transactions on data and knowledge engineering. So we propose efficient solutions for different basic primitives such as secure multiplication and secure minimum. The good thing about these works is we have also demonstrated that by taking the parallel feature of the proposed solutions, you can indeed improve the performance actually. So what we did is like we took the protocols we proposed and we implemented it on multiple nodes and ran the computations on multiple threads actually. So we don't know like whether, because of communication cost, we don't know like whether if you implement in parallel fashion, the actual efficiency gain will be like better or not. So we just want to check that. So we did some real analysis and we came to know that parallelism will definitely improve the efficiency. So I gave one example here. For example, if you want to compare k encrypted integers, for example, if you have data stored on cloud and you just want to check whose salary is highest, for example, all the salaries are encrypted. So you need to compare all the encrypted salaries, right? So what is a naive approach? You can do a pairwise comparison, right? But that is costly, right? If you have, for example, 1 million records, that pairwise comparison will be very inefficient. So what we did is like we generated a binary execution tree and evaluated each level in parallel actually. So I mean, this is also not a very novel one, but we were able to reduce the cost to logarithmic cost actually. So I'm not going into the details because there are a lot of crypto stuff. But if you are particularly interested, you can refer to these papers I gave at the end. So, I mean, though our solutions are better than existing solutions, they are still not helpful for big data applications. So big data is big data is not a new term actually, but given the growth of data, we want to handle large volumes of data. And that too, the response time should be reasonable, right? So we want to achieve that. So what we suggest to the research community is they can take these three ideas we have suggested here into consideration while developing solutions. One is like instead of proposing straightforward solutions, they can check whether there is just any probabilistic or heuristic based approaches. I mean this involves a lot of engineering stuff. So it depends on the problem we are trying to solve here. Another important observation we came to know a couple of months back is we can move some of the expensive computations to offline phase actually, because encryption is a very costly operation actually. For example, if you are using your mobile phone and if you are doing a lot of encryptions, then you will not be satisfied with the response time, right? So all these expensive operations should be avoided somehow actually. So what we are trying to suggest is not all actually, some of these expensive operations like exponentiation and those things can be computed in an offline manner actually. For example, if you are computing encryption of random value, that is independent of any values actually, you can pre-compute that value. Similarly, if you are computing encryption of 0, encryption of 1, they can be computed by the cloud in advance actually. It doesn't need to wait for the user. The cloud can compute all these values and store it somewhere. Once the user asks, he can utilize these intermediate values actually. There is no need to do again computation. And of course, we need to focus more on parallel solutions because we want to utilize the parallel processing capability of the cloud. I mean, there are many solutions that are trying to address these problems actually. But most of the solutions, they do not, as I mentioned earlier, they do not ensure proper security. They leak some kind of information. So this information, depending on the scenario, can have a very large impact. So while developing the solutions based on these 3 points I mentioned here, we also remind that the solution should satisfy the basic properties. I mean, if your goal is to develop efficient solutions or to handle big data, and if you sacrifice the privacy, then who knows, maybe may not be now, like after a couple of years, your system will get broken up actually. So you also need to have proper security while developing the solutions. So next we will discuss about privacy preserving data management. So as I mentioned earlier, there are many issues associated with privacy preserving data management, but most important of them is fine-grained access control and query processing. So the issues we need to consider is we need to protect the confidentiality of the data, and of course it should be effective. Effective means it should support all the database functionalities, and it should be efficient and also scalable to big data applications. So I mean in the past decade actually, the researchers have proposed a lot of work actually, but the most popular work is by Papa and his team from MIT. Their system is referred to as encrypted actually. It is a very famous system. What it does is like it will try to outsource the database to the cloud environment and provide regular database functionalities. They utilize a lot of encryption schemes to encrypt the data. For example, they use order preserving encryption scheme for comparison, deterministic encryption scheme for equality, and homomorphic encryption for performing addition and multiplication over the encrypted data. But there are many disadvantages with this cryptDB actually. Actually, Monomy is basically an extension of cryptDB, so there are not many big differences actually. So the first disadvantage is cryptDB allows only column level granularity, which means like the either will either get access to a column or not. We do not have any functionality saying like within the column, some of the users can access the first 3 cells, some other users can access the rest of the cells. We don't have this kind of functionality. So the access control provided is based on the column level actually. That is not true in many of the real world applications, right? Within each column, different users can access different parts of data actually. So another disadvantage is they encrypt each column with different encryption schemes. This is one of the biggest disadvantages of cryptDB actually. So one example is shown here actually. We have 3 examples actually. So each column is encrypted in an onion format actually. So consider an onion actually. So onion will have a lot of layers, right? So they will encrypt the data with a encryption scheme that guarantees weaker security. On the top of that, they will encrypt the data again with a very stronger security model. So whenever a user issues a query, what they do is like the server will peel off the outer layers, and using the inside encrypted data, it will do the operations. So to overcome this, to address some of these issues actually, there is a recent system referred to as dbmask. This is developed by one of our collaborators at Cyber Center. This is a basic overview of the dbmask. So we have a data owner and we have a cloud provider and we have a trusted proxy. Actually that is one of the bottleneck here and they are trying to avoid that. And we have a set of users actually. So I will just briefly, I won't go into the technical details, but I will just give you a high level picture of this. So what it does is like we encrypt different portions of data using some secret keys, and the data owner here, he will encrypt the data and send that encrypted data to the trusted cloud here, untrusted cloud here, and then he will also encrypt the keys, secret keys, and send that to the trusted proxy here. So the proxy here is a bottleneck, and I'm fully trusting it. It's not like semi-trusted. I'm fully trusting it actually. That's one of the bottlenecks actually. But I think the main motivation for proposing this work is they are assuming that this trusted proxy is within your premises actually. If you have a company, then this trusted proxy is somewhere within your company actually. So that's why we are placing some trust on it. But that's not the case, right? If you have that proxy in your premises and it has a lot of resources, then there is no point of using the cloud actually. I mean, it has some disadvantages and advantages. So whenever a user tries to access this database, he needs to first authenticate to the proxy. He needs to provide some kind of information that involves some cryptographic protocols actually. Once he authenticates to the proxy will be able to get some secret keys. He will use those secret keys to encrypt the query the user sends and sends the query to the cloud actually here. So the cloud then will operate on the encrypted data and return the results to the proxy, and the proxy will encrypt the data and return the result to the user. So this DB mask, since we are encrypting the data at cell level, it can guarantee fine-grained access control actually. So I won't be going into the details since we don't have enough time. So the current version we have, it supports like numerical comparisons and keyword comparisons. For example, you want to compare whether the salary of particular data record is like 20,000 or 30,000, something like that. You can do such kind of comparisons. And also if you are looking for some username, you can do keyword comparisons. So I'll just give you some example so that you'll get at least some brief idea of what we are doing. So here each cell or each column will be encrypted twice actually. The first column will be used for fine-grained access control, and the second column will be used for matching actually. So here is one example actually. So the top table shows some sample data, and the below one shows the encrypted data that we will send it to the cloud. So if you can observe, each column is encrypted twice actually. So the first column is basically the data for access control, and the second data is basically for doing comparisons actually. So here the group information is public information. So each user will be assigned to a particular group actually. Based on which groups he belongs to, the proxy will ask the cloud to restrict that query to that group actually. So we are not scanning all the groups actually. We are only restricting the query to particular records or columns actually. So basically this paper got accepted at CodaSpy recently. So if you are interested, you can just, I think it's available online, so you can just quickly go through it. So here we have some research directions for PPDM. So the current version of DB mask, it only supports additions and keyword matching. But DBMS has many more operations, right? We need to have joins. Join is a very complex operation, and order by, those kind of things. And doing those kind of operations on encrypted data, it's very hard actually. It's not hard actually, but it will be inefficient actually. So we need to come up with some new solutions. So, and of course, as I said, in our DB mask, the proxy is bottleneck, right? Because we are trusting the proxy. So how to improve the privacy requirements of current version? And also we are leaking some information to the cloud. For example, if you look at the example here, if the cloud compares two values, it will know whether they are same or different, right? Even that kind of information can be useful to the cloud because it can leak access patterns to the data. So we need to do some privacy enhancement to the DB mask. And of course, we need to develop scalable solutions for big data. I think the current version, not only this DB mask actually, most of the solutions out there, they do not talk about big data actually currently, because we are not currently into that stage actually. This is a future research actually. We need to develop more solutions for big data. And of course, it needs to support other DBMS functionalities such as delete, update, and all those operations, like user revocation and all those things. So privacy preserving data analytics. So privacy preserving data mining, this is a very old problem. It was proposed in 2000 or 2001, I guess. So what they are trying to do is, like, we have a set of users, and they are collaborating with each other trying to solve a data mining problem. Each user will have some data actually, and they don't want to reveal their data to the other party, but they want to compute some functionality like clustering actually. They want to only get the final result without revealing their data set. So the solutions based on privacy preserving data mining, the user has to do a lot of computations, and it also involves a lot of communication between the parties. So what if I'm dealing with a big data, or what if my machine doesn't have proper resources? So what is the alternative? I cannot involve in the these solutions, right? So I need to come up with alternative solutions. So that's why we are coming up with outsourcing the entire task to the cloud, because cloud has a lot of resources, right? But again, it is not that easy actually. Operating or analyzing on encrypted data is not so easy actually. But basically what we are assuming is these are not real-time applications, because most of the solutions out there, they will take like 1 day or 2 days. If that is fine with you, you can use these kind of applications. But if you are talking about real-time applications, then as far as I know, there are no solutions out there. There are some solutions to clustering, classification, and association rule mining. As I said, they are still not suitable for big data applications. I mean, if your data doesn't contain any sensitive information, you can just send a plain text data, right? You don't need to worry about privacy. But in many cases, we need to concern about privacy issues, especially if you are dealing with patients' data from hospitals, any business data from credit cards, even government data actually. That is also private actually. So we can have different models here. So this is one basic model we are trying to propose as an initial approach for PPDA actually. So we have a client here who wants to do the data analytic task. So what he will do is like, he will encrypt the data and send the data to a database server here. And we have a set of another servers actually. These servers will do the data analytical task actually. Because data analytic task, it's a more complex problem. So doing the task by single cloud is almost difficult actually. So we need to ask so many clouds and use their resources to perform the task. So basically, the user will encrypt the data and store it on the database server. Then what is these servers are for? So we are encrypting the data, right? So we are using some key for that. So what the user will do is like, he will split the secret key and share each part of the key with each server actually. So for example, if I have like 10 servers and I have a secret key that I use to encrypt my data, I will split the secret key with 10 shares, and I will send each share to one of these servers actually. So the servers will use these shares and the data stored here, and all these things, this entire thing shown in the cloud, it's from the cloud side actually. So all this, the DB server here and analytical server here, they will do the task because they got the shares of secret key. But we need to have some kind of assumptions here, right? Because all the shares are provided to the servers. So we need to assume like at least one of the server is honest actually. Otherwise, all the servers can collude and they can construct the secret key and they can ask the DB, they can get the actual data actually. So we need to assume at least one of these servers here is honest, which means like he did not collude with other servers. So that is the model actually. Using that model, you can solve a lot of data mining tasks actually. So one of our collaborators have recently proposed a solution for association rule mining. So association rule mining is a very famous data mining task, right? So here is just a brief overview of that idea. So as part of the initialization, the user will generate some public secret key pair based on algorithm encryption, and he will divide that secret key into n pairs actually. So here I am assuming we have n data analytical servers. He will encrypt the data using the public key PK and send the encrypted data to the database server. So database server is basically like for managing the data actually. He won't be doing much work actually. Most of the work will be done by the data analytical servers. So once I send the encrypted data to the cloud and the analytical servers will somehow has to communicate and find out the frequent item sets. So finding the frequent item sets is an important step in association rule mining. So once they do the computation, the final output should also be in encrypted format, right? Otherwise, they will know some information. So the final result will be sent to the user, and he wanna decrypt the data and get the values. So actually, this is a very basic high-level view, but there are a lot of steps actually. There are a lot of cryptographic steps involved actually. So, I mean, very recently we got a paper accepted at IEEE Transactions on Knowledge and Data Engineering. So it deals with the classification actually, how to do the classification task over cloud actually. So we are outsourcing the classification task to the cloud. The solution utilizes a lot of cryptographic primitives as building blocks, and also we utilize parallelism actually. So one example is shown here. So if you look at the bottom layer actually, so this is the bottom layer. So here I have like 6 encrypted values. This bracket denotes encrypted value actually. So I have 6 encrypted values, and out of these 6 encrypted values, I want to compute the minimum value. So what can we do? Like we can do pairwise comparison, right? Like this. First I can compare this, I can compare this, I can compare this. But I can do that in parallel, right? I don't have to compare the secure minimum out of this and utilize this result with this. I can do that in parallel actually. So we did this implementation on multiple cores, and we found that I think we utilized like 6 threads actually, and the performance improvement was almost like 5.5, something like that. So that shows that parallelism will definitely improve the efficiency. But we did experiments only on single node. But if you run the experiment on 1000 nodes, perhaps the performance will be very efficient. But we also need to take consideration like network latency and all those things, especially in cloud actually, because so many people will be using the cloud. So, but still I think it will be very efficient compared to serial execution. So I'm not going into the details again because there are a lot of crypto stuff. But if you are interested, you can talk to me after the presentation, or you can just go to the link provided here. I think the paper is available to everyone. So similar to privacy preserving data management, the efficiency of privacy preserving data analytics depends on underlying basic primitive types. For example, here we have the classification. One of the important tasks in classification is we need to do secure comparisons and find the minimum values, which means like the secure minimum protocol I am using in the back should be very efficient. Otherwise, the whole protocol will be very inefficient. So we need to identify what are those basic constructions and develop more better solutions actually. So I mean, we just in the current work we have only solutions for classification and association rule mining. But however, like there are a lot of data mining problems, right? It's not like people will just use classification or association rule mining. We have a lot of data mining tasks that people want to outsource to the cloud. So we need to develop, because each task will involve different computations, right? So we have to develop customized solutions for each task. So, but they will have some overlap, but we need to come up with a efficient strategy while implementing it. So, and of course, I think most of the works we have until now, they do simulations actually. They do not do actual implementations. Even we didn't do actual implementation because it is very hard to control on the real cloud, right? Because they are maintained by Amazon and those guys, and it is very hard to control some parameters actually over there. But hopefully, I think in the near future, like people will develop better solutions and they will do real prototypes, implementations on the real cloud. For example, if you are using like n different servers, that servers can be on multiple clouds. For example, one on Amazon, another one was like Microsoft Azure actually. So we cannot do that. I mean, in current scenario, we cannot do that, right? I cannot go and ask Google, and I cannot go and ask Amazon, okay, I want to run some experiments. Can I utilize your servers for that? It's very hard actually. So conclusions. So big data, I mean, cloud computing is one of the natural choice actually, but you don't need to use cloud computing. But the only reason we are trying to focus on cloud computing is it has a lot of resources, which is a important thing for handling with big data, right? So that's the main reason why we are focusing on cloud computing. So the open question to all of us is, how can the cloud manage and store and analyze big data in an effective, efficient, and privacy-preserving way? So in this talk, we just discussed two important problems like privacy-preserving data management and privacy-preserving data analytics. I mean, the research in these two fields is still in initial stages. So I think, I mean, as I said, like the US government is involving a lot of funds into these projects. So hopefully more people will work and come up with better solutions. So as part of the future work, we are currently also working on other data mining tasks like clustering and all those things. We are developing parallel solutions actually, but still I don't think that will be useful for big data applications, but they can be used in most of the current applications. And while developing the solutions, we also need to take a lot of engineering details, like as I said earlier, we can pre-compute some of the computations. We don't need to compute everything in an online fashion actually. So that will be the focus actually, like how to improve the current research in these two areas. And I mean, in this talk, I mentioned that we are assuming the data is encrypted, right? But encryption is not the only way to protect privacy actually. We can transform the data using so many other ways and send this transformed data to the cloud actually. So we also need to consider those techniques and see whether those kind of techniques will be more efficient than encrypted based techniques actually. So some of the techniques will include like secret sharing and anonymization actually. But basically anonymization, it won't guarantee better security. But I think secret sharing based solutions will give rise to better, more efficient solutions actually. So we have to do a lot of research in that direction. Otherwise we cannot have proper or concrete conclusions. So that's for today's talk. So if you have any questions, please. Yeah, please.
So you were referring to big data. You're referring to big data. So big data is commonly associated with NoSQL data. Are you using any NoSQL data for the privacy preservation that you're doing in your experiments? Because, for example, if you take Hadoop or Spark or any of these systems, you have data blocks that are actually subsets, logical subsets that are actually analyzed, processed, transformed, however you want to take it, by specific machines. You actually don't have to partition it to send it to multiple machines. I mean, the data is already partitioned. So have you used it? Because one of your examples was talking about, encrypting one of the vectors, which is basically a column. So my guess was it was towards the SQL side. Not sure if...
I mean, data integration actually. So because we are collecting data from multiple sources, right? So that's the job of data owner actually, first of all. Because he is collecting the data and he has the data. He has big data actually. So he has to represent the data in a single, in a structured way before outsourcing actually. Then the cloud can utilize existing frameworks such as Hadoop and Spark. That's a different task actually. That's for how to manage the data on the cloud. But before outsourcing itself, he has to, because data will combine from, for example, if we have data from sensors, that will be maybe XML file. If you have data from other GPS, that can be normal textual file. So this data integration, there are many tasks actually, but my focus is mainly on privacy actually. I am assuming the data is in particular format, like SQL actually, but I think most of the solutions can be applied for textual data and other data sets actually.
I mean, what I was actually wanting to know was, so you must have applied your solution to some form of example data set. So is that a SQL data set or is that a NoSQL data set?
We consider SQL data set actually.
Okay, so that's an example set. You haven't done any NoSQL, which is commonly associated with big data.
No, actually.
Okay.
So because once the data owner collects the data, he needs to represent in a standard format, right? That will also be used.
I mean, standard format does exist. I agree with you, but the thing is, NoSQL has this inherent feature that you don't have to create a structure for the data. I would not want to use the word free flowing, but for the lack of anything, for the lack of a word, I'm going to use it here. It's more flexible in terms of how you can set the data.
Yes.
And which is why I was wondering, if you're looking at solutions which might be towards.
So it depends on the task. For the privacy preserving data management, SQL is the most common.
Okay.
So we just consider SQL data sets.
Okay, sharing SQL, makes sense.
Yeah, for data analytics, it can be most of the times it is testable data sets actually.
Okay.
So we need to do some pre-processing actually. We can do that on the cloud actually. We can use some vector space model and those kind of things. That can be done either by the data owner or cloud. But I think since cloud has resources, but again it's difficult, right? Because you need to encrypt the data and send the cloud. For extracting the features, you need to have plain text data. So most of this process, pre-processing should be done by the data owner, not the cloud actually, for privacy reasons.
Thank you.
But for analytics, we can have different variations actually.
Okay, thanks.
Any more questions? Any more questions or even suggestions are welcome.
All right, thank you.